We're getting closer and closer to being able to solve an actual integral involving partial fractions, but the piece we need now is actually how to split out the partial fraction decomposition. Now I'm going to do one that's a little harder than what you would normally do because I want to show you that this can get kind of ugly kind of quickly, but the method's going to be the same, so hopefully it won't lose you too quickly. So to review, remember we can use long division first to get it in the form we need, and then we need to factor the denominator, and then we'll separate the linear factors, separate the quadratic factors, and finally we'll solve, and that's what we're trying to do in this particular video. So given this example, 27x cubed minus 44x squared minus 68x plus 15 over what is already a factored denominator, 3x minus 7 squared, x squared plus 2x plus 10. I want to go ahead and do that because frankly, as you can see, the board's already pretty full, so I don't want to overload it too much. So the first thing is we don't need to use long division. And this is a really good example of why. You look at the top and you say, well, that's x cubed and there's no x cubed down here. And that's true. But the reason being is that if you were to multiply this out, that would be degree 2. And this is also degree 2. So when you multiply those together, you end up with a degree 4 polynomial. So since the bottom is actually degree 4 and the top is only degree 3, we don't need to use long division. So that's a mistake that can happen. So just be aware if it's already factored. The second thing is to factor the denominator. Well, that's already done. So what we need to do now is separate the linear factors. So when you look for linear factors, what you want to do is look for any grouping that looks like that sort of that line equation, right? That's why they call it linear. So it's sort of like mx plus b kind of format. So in that form we say, okay, I have a 3x minus 7, and it has a multiplicity of 2. So since it has a multiplicity of 2, what we do is we say, all right, I take the case where it's multiplicity 1, and I take the case where it's multiplicity 2. So I do that one all the way up to squared. If this had been a cubed, I would have had another term like a c over 3x minus 7 cubed. If I had a c here, then I wouldn't have a c there, by the way. It would just keep pushing. But so I have an a and a b. Notice that those are both just constants. I don't have like an a and an ax. That doesn't work that way. So that takes care of my linear factors. However, I have this factor. Now, you can verify this for yourself that this is not factorable. A good way to verify whether or not it's factorable is to, if you were to plot this and to graph this, you would notice it never strikes the x-axis. It's always above it. Another way to do it would be if you use the quadratic formula on this. The quadratic formula would not give you real solutions. It would give you complex valued or imaginary solutions. And so, as a result, you know that it's not factorable over the reals. So, we need to take this. Now, it only has multiplicity 1 because there's no extra number there. So, we end up with cx plus d over x squared plus 2x plus 10. So, remember that's, if it's linear, you have a 1 degree less, so that's degree 0. This is quadratic, you have 1 degree less, so that is cx plus d. Now, if we're going to solve it, the thing we've been waiting for, the first thing you want to do, and this sounds odd, but we're actually going to multiply both sides by the denominator. So we're going to multiply everything by this grouping here. What that's going to do is that's going to eliminate the denominator on the left side, and then it's going to have cancellation for each of these groups. So for this one, and let's not even focus on this one first. For this one, I have this factor. So what's left over is that 3x minus 7 squared. For this one, I have a 3x minus 7 squared, so what's left over is this term after cancellation. And then for A, I only have one of the 3x minus 7s, so I have one left over, and I also have the quadratic term left over. So now I have some equation equals another equation. And that's true, just generally across the board. Don't worry about the domain restriction stuff right now. In fact, we're going to exploit that. So I have this and that. And what I want to do is I want to narrow this thing down so that I can figure out what A, B, C, and D are. So what I do is I'm going to pick convenient values of x. What is a convenient value? Well, generally speaking, what you do is you want to start off by plugging in values that completely wipe out terms. So if I look here, I say, all right, what value of x would completely wipe out this term? Well, it's actually going to be the 7 over 3, but we're not going to do that immediately because that's kind of ugly to plug in. But if I plug in 7 over 3, this whole term would wipe out, and this whole term would wipe out. So you'd actually only have this term, and then you'd have to plug it in over there. So that would allow you to get some number over here, some number times b over here, and then it would simplify. But we're not going to do that because I want to also talk about other convenient numbers that are common to use. So if you have just linear terms, you can usually exploit, using that, like that 7 over 3 and all that stuff, and it works out really, really well. But if you have quadratic terms, it's a little more complicated. So some of the other common terms to use are like x equals 0. The reason why x equals 0 is very convenient to use is that it'll wipe out every term with an x. So like, and then it'll even wipe out that c term, which is a little problematic, but we'll get back to it. So if I use 0, this whole thing gets wiped out and I'm left with 15, and then that becomes a -7 inside and a +10, and then that's just a +10, and then the c gets wiped out, and then that becomes -7 squared. So what that does is it reduces to this little smaller compact equation, which isn't that helpful to us right now, but we'll get there. The next piece is when we use x equals 7 over 3. Now this takes a long time to do, this particular one. I kind of chose this example poorly, to be frank, because it takes a lot to simplify, but you can get there. If you plug in 7 over 3 into x, and then x cubed, x squared, x, and whatnot, you just keep plugging in 7 over 3, you get a bunch of stuff here, plus 15, and then again, everything on this side dies, right, because it vanishes, except for the b term, so you end up with this piece. Now, if you run all this number is equal to all that number, and you simplify and divide and whatnot, you actually get a kind of a nice answer. B is equal to -2. That's not too bad. B is equal to -2. So if B is equal to -2, then what I can also do is I can plug it in here. So I have 15 equals -70a minus 20 plus 49d. So then if I have a minus 20, if I add 20 to both sides, I get this. 35 is equal to -70a plus 49d. And if I divide both sides by 7, I get 5 is equal to -10a plus 7d, which I'm then going to rewrite 7d equals 5 plus 10a. So what I'm doing is I'm using that to shrink my problem. 7d equals 5 plus 10a. The next term, x minus 1, or x equals 1. So this is another convenient value. It doesn't cancel anything, which is not that helpful, but what it does do is instead of having to square things or cube things or whatever, it essentially turns all of the x terms, all the coefficients into just the numbers, right? So now I have 27 minus 44 minus 68 plus 15, and then, all of this simplifies here to very, very convenient terms. It doesn't blow up anything because all the x values just become 1s. And by simplifying that again, I get this. Now I have a relationship of d to a, so I can plug in there. I can plug in for d. And so the d will turn into a's and some change. And by simplifying this equation, I'll get 28c is 51a minus 97. Now I hit a lot there because again, there's only so much board space, and I'm kind of expecting at this point that your algebra skills are good enough that you could take this, plug in here, and simplify this out. Maybe I've misjudged you, but I'm counting on that. Now finally, x equals -1 is a typical convenient value because it does the same thing as x equals 1, it just swaps signs. So instead of 27, you get -27. It doesn't swap the sign on squareds, right? Because -1 squared is just +1. So you get very similar setups to how you have here, except for the cubed and the non-cubed terms, it's that. And then instead of 3 minus 7, which is -4, it's -3 minus 7, which is -10. So you get very similar behavior. When you multiply all that through, you get 30 is -90a minus 100c plus 100d. So now what we know is we can, instead of d's, we can turn it into some number plus a. Instead of c's, I can turn it into some number plus a. So I have just a's and just numbers. So if I simplify that whole equation, I get that a actually equals 3. So now I know that a is 3, and I know that b is negative 2. But c is in terms of a, so I plug in 3 here and solve. That tells me that c is positive 2. I plug in a here and then solve. So, 7d is 35, so d is 5. So what does that tell us? That tells us with those 4 numbers, I can fill out this equation giving us 3 over 3x minus 7, negative 2 over 3x minus 7 squared, and 2x plus 5 over x squared plus 2x plus 10. And so that's how you would take that and do some partial fraction decompositions. Now we're going to do some more problems other than this, but I wanted to show you one that was a little more complicated because I wanted to show you that it's not always super straightforward even when using this method.